This is section 3.2, derivative as a function. The derivatives below, or the definitions below, should look somewhat familiar from 3.1. This is how we were defining the derivative at a specific point. And so we actually had two options. The first looks at the limit as x approaches a of f of x minus f of a over x minus a. And that should look familiar from sort of like the slope equation, right? Rise over run, the change in y values over the change in x values. And there was another option, which was to look at the limit as h approaches 0 of f of a plus h minus f of a over that value h. And that's the one that we're going to be focusing on today. But instead of looking at a specific point, x equals a, we're going to look at it for just a general x. And this would be useful if you're trying to compute the derivative at multiple points. As we saw, there's a lot of algebra involved. And so you don't want to have to go through and do all that simplification, all that algebra for multiple points. If you're trying to compute the derivative at a equals 1 and a equals 2 and a equals 3, that can be kind of a pain. Okay, so here we see the definition of the derivative function instead. Instead of taking x equals a, we just look at any old x. But we can see that otherwise it looks pretty much the same as what we had before. We're still looking at the limit as h goes to 0 of f of x plus h minus f of x over h. So what will be different is as you're simplifying, you'll have an x term now instead of having that a term that you had already plugged in. So let's do an example. Let's see. What if we're trying to find the derivative of the function square root of x? And let's say we wanted to actually compute this at various points at x equals 1, x equals 2, x equals 3, right? We don't want to have to use this other original definition and do all of the simplification. So let's take this formula here and go ahead and plug this in. Okay, so when we plug in x plus h to our function, we get square root of x plus h, that whole quantity, minus square root x over h. Now, you should be quite familiar with the limit laws. So what happens, Dan, here? Can we just go ahead and evaluate this limit? Can we look at the numerator and the denominator?
Well, we have to check both and see what happens first. So we have to see, can we use the limit law? So if we check the denominator, it's just h. So if we split that off, that's going to be just 0. And then we check the numerator. Well, that looks like it's going to be, h is going to 0, and then you just have square root of x minus square root of x. That's just going to go to 0 too. And we already know that's called an indeterminate form. So we're not allowed to do that. So we can't do limit laws right now.
Exactly. Yeah, splitting up the quotient that way only works when those limits exist, and they don't in this case. You can't have, well, I mean, the limits exist, I guess, but the denominator, the limit is 0, and so that's something that's not allowed. So what we'll do instead is we'll use the trick that we used back in the limits chapter, which is multiplying by the conjugate. So we can multiply by square root x plus h plus square root x, and the same thing in the denominator, so that it's like we're multiplying by 1, right? That's what makes it okay. We're multiplying by the same thing in the top and the bottom. And that looks like it's really making the problem worse. But thankfully things will, what'd you say?
But it's not really making it worse.
Right. Thankfully things will simplify. So if we, let's look at what's happening in the numerator. So if we take this term times this, what that really looks like is it looks like you're multiplying a minus b times a plus b. And if you recall from pre-calculus, when you use FOIL, those middle terms, the AB and the BA terms cancel out. So what you're really left with is you're left with that a squared minus b squared. And so that's what's going to make our lives a lot easier. So we have to write the limit every time. Limit as h approaches 0. And then in the numerator, what we'll have is we'll have square root x plus h, but that whole thing gets squared. And so we actually, so if I write that, those will actually basically cancel out, right? We'll be left with just this term x plus h. And then the same here, we'll have this square root x term that gets squared. And then in the denominator, we'll have h times this whole mess. Okay. So what this becomes, again, you have to write that limit every time, is we'll have x plus h minus x over h. And again, just sort of keep this whole mess down here. We can't really do anything about that right now.
Yeah, it'd be so nice if we didn't have to write it every time, but we do have to write it every time.
Yeah, exactly. Okay. And what's great now is in the numerator, those x terms cancel. We have plus x and we have minus x. And so then we're just left with h. And at this point, we can see the finish line. We can see that we're almost done because we can see that these h terms cancel. If we were to go ahead and try to take the limit now, we'd run into the same problem. We'd have 0 divided by 0. We don't want that, right? But now that they cancel, we have 1 in the numerator, and then we have this square root x plus h plus square root x in the denominator. And what happens now, Dan, when we plug it in?
Well, when you put h going to 0 in the denominator now, like you would in limit laws, denominator is not 0 anymore. So you just have 1 over square root of x plus 0 plus the square root of x.
Exactly. So 1 over 2 times the square root of x. And what's great now is this is a function. And if we wanted to find the derivative at specific points, like if we wanted to find the derivative at x equals 1, for example, we can plug it into this function. And we get 1/2. If we wanted to find it at 2, we get 1 over 2 times root 2. And so we don't have to go through all of that algebraic simplification every single time. We can plug in lots of values now. And we can even graph the derivative also, which will be very useful. Stop recording.